Yes.
Okay.
My
Shall
name
I
is Oleg Groisman. I am from Israel, and we begin our first session, T07, Dynamics of Living Systems. And we have three presentations during yes, from three scientists from three countries. The first presentations is because each presenter has very big, not short biography. Yes, therefore I shortly say about the first Soumya Banerjee from the University of Cambridge, UK. He will present the lecture, a roadmap for a computational and informational theory of life. But I see this is new name, new title, Life as We Do Not Know It. Yes, please, Soumya.
Yes. Shall I start?
Yes, Soumya, go ahead.
Yes. Thank you so much. I did change the title, and if people are not able to hear me, please let me know. Again, thank you so much for having me here. I changed the title to Life as We Do Not Know It, as opposed to Life as we know it. What I will do is I would like to start off with a short story, and I promise you that at the end of hopefully 10 at the end of hopefully 20 minutes, I hope to give all of you a different perspective on life. I'll start with a short story, and the story actually starts in
Soumya, can you make it full screen if you want? It's up to you.
Okay. Can you see it now better?
Yeah.
Is that?
Yeah.
And the story actually starts in Boston about 6 years back. In the winter of 2014, I was in Boston, and I'm not used to seeing so much snow, but that particular winter, there was a huge snowstorm in Boston. And I remember I was stuck in my house for 2 weeks, and the entire city had shut down. And since I'm very fond of science fiction, I had just got a huge collection of science fiction books from the public library to actually read. And I remember I was staring outside my house window, seeing about 8 feet of snow and thinking, how will I ever get out of this? And I chanced upon a very old short story, and I was reading a very old short story by the science fiction writer Arthur C. Clarke. He had written a short story in the 1950s named Crusade. And I remember sort of leafing through this very well-thumbed copy of, I think, almost a first edition book that he had written. And there was this particular short story named Crusade that he had written in the 1950s. And the effect that it had on me was absolutely profound. I felt like I had been hit by a sledgehammer, and my complete perspective on sort of complex systems, dynamical systems, and life really sort of changed. What I will do is I'll take the slight risk of playing probably a minute of the short story, and I hope that the audio will come through. This is literally a 12-minute audio that you can listen to online. Links to this are available on my link here. But what I will do is I will actually play 1 minute of this short story just to give you, hopefully give a sense of that perspective to you.
It was a world that had never known a sun. For more than 1 billion years, it had hovered midway between two galaxies, the prey of their conflicting gravitational pulls. In some future age, the balance would be tilted one way or the other, and it would start to fall across the light centuries down toward a warmth alien to all its experience. Now it was cold beyond imagination. The intergalactic night had drained away such heat as it had once possessed. Yet there were seas there, seas of the only element that can exist in the liquid form at a fraction of a degree above absolute zero. In the shallow oceans of helium that bathed this strange world, electric currents, once started, could flow forever with no weakening of power. Here, superconductivity was the normal order of things. Switching processes could take place billions of times a second. for millions of years with negligible consumption of energy. It was a computer's paradise. No world could have been more hostile to life or more hospitable to intel.
A little bit of that audio came through. I'll pause the audio. I'm not sure how much of that audio really came through. But here in the story, written in the 1950s, Arthur C. Clarke is imagining a cold, lifeless planet that is stuck between two galaxies. It's in the void, and it's absolutely insanely cold. It's barely a few degrees above absolute zero. And yet, he imagines life thriving on this planet. And this is naturally fictitious, but he imagines liquid helium that has attained superconductivity, and there are electrical currents that are being driven through the superconductor. Ultimately, this leads to neuron-like networks that are capable of superhuman, exceeding human intelligence. Naturally, he proposed a completely different computational substrate in this story, electrical currents and superconductors, which is radically different from think of room temperature, carbon-based life forms, which is what we are. And it really challenges our imagination, and probably it's probably infeasible, but really what it does is it challenges the very notions of life as we know it. And really what I argue for in my talk is that perhaps we need to be more sort of open-minded. Mathematical principles coupled with a mathematical definition of life, rather than only what we see on Earth, would better prepare us for life or lifelike forms that may exist anywhere in the universe. I'm not suggesting that we completely disregard data, that is whatever we see on Earth, carbon-based life forms, but merely that we keep an open mind and use sort of objective criteria for life. As a slight detour, I mean, hopefully none of the audience will be sort of strangers to sort of complex dynamical systems, but one that I like to sort of pick on is the reaction diffusion system, this Belousov-Zhabotinsky reaction system, which, as many of you will know, but for those of you who don't, it's a real life system of chemical oscillators, very, very simple rules that are encapsulated in it, and that can actually, that displays complex properties that are reminiscent of life. What I will do is, and please let me know if this simulation isn't coming through, I'll just quickly set up a brief simulation of this, and then I will hit go. Is this, can everyone see my screen here also? It says BZ reaction.
Yes.
Okay, great. So naturally there are two chemical species, and they are interacting both over short and long distances. And one can see patterns sort of evolving over time. And these mesmerizing patterns are, I mean, very, very similar to sort of life forms. One can, if one stares at these long enough, one can see outlines of possibly even cell-like features, features like sort of plasma membranes. And if I let it run long enough, which is what I will do, I'll go back to my talk, you will see sort of standing waves that are coming up, persistent patterns that persist despite sort of random noise and perturbation. And as I'm speaking, you can see some persistent patterns that are coming up here, which are very much reminiscent of life. And so I really argue that there can be sort of novel non-carbon based computational substrates. I mean, here we have looked at a very simple chemical oscillator, and these may have lifelike properties. In yesterday's talks, for example, there were a few mentions of naturally oil droplets, systems of oil droplets that exhibit lifelike properties. They are able to replicate and consume energy. And naturally oil droplets have also been engineered to have compartments and derive propulsive power from an external energy source. And again, these are quite different from carbon-based computing solutions. To take this idea a bit further, and this is, I'm asking you to take a leap of faith here. Stars also have an internal energy source, and they have compartments. There is sort of a clear delineation of where the star begins and where there's space outside. And disturbances from stars, for example, some stars will undergo supernova, not all, at the end of their lifetimes. And this is a massive sort of a very cataclysmic event that can perturb sort of interstellar clouds and nebulae, which are close to that. And that leads to further sort of star formation in that neighborhood, in that galactic neighborhood. And this can be thought of as conceptually similar to replication. This is a dynamical system that exists for a really, really long time, millions or billions of years. And at the end, when some of these do undergo supernova, there's this cataclysmic event that perturbs the local neighborhood and then causes more star formation and hydrogen cloud collapse, which leads to more star formation. This is, I argue that this can be thought of as similar to sort of replication. Going back to sort of spherical droplets, things that are much closer to Earth, self-propelled colloids, and even motile crystals move about in remarkably lifelike ways. And as I think somebody even yesterday pointed out, that there are these systems of microscopic beads of artificially engineered materials that exhibit swarming behavior under the influence of an electric field. There are also quantum systems that are capable of transferring information like spin. So spin is a very unique characteristic of quantum systems. And they have also been, and these quantum systems have been proposed to have lifelike properties. And coming back to, I think, my favorite sort of system here are weather-like systems like hurricanes that persist for really, really long times. There are, for example, weather systems on planets like the Great Red Spot on Jupiter that has persisted for a very, very long time and displays very, very complex properties. It's sort of motile and moves about. It is fairly robust to sort of external perturbations, and it really persists for a very, very long time and displays very complex properties. So I guess, I mean, going back to my sort of main theme here, that I propose that having an objective definition of life rather than only what we see on Earth might better prepare us for life or lifelike forms that we may hopefully encounter elsewhere in the universe, hopefully sometime in the future. And I propose here as a very preliminary set of list of criteria that may fulfill this criteria. And again, this is open to discussion and debate, and I don't mean that this should be an exhaustive list. I only mean to sort of engender and start a discussion around what objective criteria could be there. And since I'm a computer scientist, my first point in there is really about information processing. I mean, much of it, if we see these complex dynamical systems, these nonlinear dynamical systems through the lens of information theory, these can be thought of as sort of processing information, which is, if I put on my computer scientist hat, that's really the software. There's also information storage. I'll have more to say on it later. And naturally, the physical substrate, the hardware, is immensely important. It does not, I think it doesn't need to be only sort of carbon-based life forms operating at room temperature, as the quite imaginative story by the science fiction writer sort of showed us. I mean, there could be other substrates that are out there that it would behoove us to really open our minds to. And definitely, once we talk about physical substrates, the role of physical space is, I think, quite important. I think some of these lifelike systems will also need to have information transfer across both physical space and time. And naturally, there needs to be persistence of information, that is selection and heredity, and energy and thermodynamics, which is why I'm here, I think is a key tenet. It needs to be a key pillar on this in this sort of framework. There needs to be energetic limits on information processing and life. So for example, in the BZ system, there are certain model parameters that lead to persistent wave-like patterns. One can see these wave-like patterns right here that seem to persist even though there is a lot of perturbation and noise in the system. And these may become dominant. And some of these may have selective advantage, which is why going back to this persistence of information, this is really similar to sort of selection and heredity. Some of these parameters that lead to persistence may need to be sort of transferred both across space and time, that is your sort of offspring, quote unquote. Certain features of information processing, I think, could emerge faster, and the rate of information processing itself may be faster based on the energy or temperature of the system. This is going back to the thermodynamic angle. And there may be an optimal range of energy and temperatures for information processing to be viable. Actually, too cold and molecular motion would cease, although as the story can demonstrate, you could potentially have quite complex lifelike patterns, barely a few degrees above absolute zero. And naturally, too hot and critical physical structures that are capable of sustaining information processing would dissociate faster than they would arise. I just want to do a quick time check. How much time do I have left?
It's okay. 4 minutes. 4 minutes.
4 minutes. Okay.
4 minutes.
Okay. And so I really argue that I think thermodynamics may play an important role in the evolution of life and lifelike systems, and whatever theory that we do come up with, I think a worthy goal in that theory would be to really unify thermodynamics and information processing under a common framework. And I think there have been a lot of discussions already, a lot of work has been done, but I think we are still some way away from actually unifying that and getting at that final goal. What I have done is, I have along with the teacher who's also my wife, we have created a lot of teaching resources around this just to get these basic ideas across to children who may be in schools or college undergraduates or even graduate students, getting these across, building sort of small assignments and sort of reading material around this. I've left the link to the story here. It's a 12-minute read that I highly recommend to anyone. Please go ahead and look at it. Very quick takeaways. I think I would like to, I hopefully have convinced you, but again, this is open to discussion, that one can think of life as computation on hopefully any kind of substrate, any kind of physical computing substrate. And hopefully that one gets a lot of perspective by viewing life as a continuum rather than just a binary decision, this sort of artificial, I think, in my opinion, this artificial divide between inanimate objects and animate objects. One gains a lot by viewing life as a continuum rather than this. And some of the properties I've already sort of mentioned here, sort of information storage, transfer, and naturally thermodynamics. This is my last slide. And what I would like to do is, if for any of you who listen to me, I would like you to close your eyes and imagine a situation. Many thousands of years in the future, humanity has journeyed to the stars. This particular star is really, really far away. You're close to a galaxy, but really far away. There's a cold, lifeless planet, and you just happen to do a stop there. And you think life possibly could not exist here. It's so cold, it's barely above sort of absolute zero. How could life exist there? And magically, you see this creature, quote unquote, that is essentially liquid helium with currents going through it, and it has superhuman-like intelligence. Given what we know now, as of today, do you think you would recognize it as life? If not, how do we need to start viewing life? What other computational frameworks, what other theories do we need to build in order to recognize life as we do not know it as life? And I think sort of information processing and thermodynamics would play a big role in that. And I think life may exist as a continuum. This is subject to debate and naturally subject to either falsification or proof by experimentation and further debate in the true spirit of scientific inquiry. But I think viewing life as a continuum, we get a deeper appreciation of the immense beauty and life that exists in our universe. Thank you so much.
Thank you so much, Soumya Banerjee, for your beautiful, interesting, and useful presentation. Yes, I'm sure that the presenters, attendees will have some questions, but we should go. Yes, we should go